science, psychology, physiology, as well as engineering and computer science. And it has to do with the acquisition, it has to do with the display, it has to do with the context, the history of the user, the end user ourselves, and so on. So what I'm hoping between today and next lecture is to at least go through some of the fundamentals in image quality assessment, what that topic means, what are the different things that we have to focus on whenever we talk about image quality assessment, and then the overall concept of quality in images. And then we'll look at subjective testing versus objective measurements, and how we can come with some mathematical measures that can give us an approximation of the subjective measures. And then we will talk about some of the ways that we can validate some of the measures and some of the tricks that are out there whenever we talk about validation of image quality assessment. So today mainly we'll talk about IQA, in short, the fundamentals of image quality assessment. And then next lecture we'll talk about design, verification, and validation of image quality assessment. I put on Canvas a number of really links to papers. Some of those papers we'll talk about in today's lecture or next week's lecture. And some of them, some of those papers are the subject of one of the topics in the term project. So we'll start with some introduction, look at the difference between subjective and objective quality, and then look at some quality assessment methods, different categories and classes of these methods, and then specifically study PSNR and SSIM. And then we look at the general framework whenever you want to create a quality measure that has HVS component to it. And we'll look at some of the examples, mainly the PSNR-HVS and the PSNR-HVS-M, and briefly on the FSIM. So definitions first. There are three different terms: image quality assessment, image aesthetics assessment, and image fidelity assessment. Image quality assessment is the whenever we have a degradation in the image. So you can imagine in this assumption in here, we have an image that really has no distortion in it. And then there was some processing on the image that resulted in some artifacts, some degradation in the quality. And that means we have two versions of the same image, and we're really trying to find or measure the quality. In the image aesthetic assessment is really more about the image, the visual appeal of it to the human eye. And this is a topic that we will not study in this course, but it's really highly related to the image quality assessment, because at the end of the day, it's the human who's really evaluating either the quality or the aesthetic component of it, the appeal in the image. And then finally, we have the image fidelity assessment, which really has to do with the accuracy in reconstructing an image with respect to some original view. And this can be more related to multi-view, stereo cameras, and so on. And we will not spend time on that one. So the focus will be on the image quality assessment measures throughout the lecture today and next week. So again, we have some degradation, it can be distortion, it can be noise, it can be artifact or some processing. And then we are studying what the difference between the degraded image and the original reference image. And it is very obvious, why do we need that? So if you look at in many of our optimization algorithms, we need to have some kind of a reference. We have the reference image with no degradation, and then we have the processed image. And you can think of these pairs as the easiest one is really in compression, for example. when you capture the raw image or the raw video, it has the highest quality because you have not done any compression on it. Once you compress it, either for storage or for transmission or for posting online, then you are reducing the number of bits to represent that image or those pixels, and that will result in if it's a lossy compression. We'll talk about those in more detail later when we talk about coding. There's a lossy compression. That means you lost some information, you lost some part of the image content, and that means there is a degradation in the quality. How much of that degradation is there? We need some kind of a measurement of that. Denoising is another example, enhancement is another example, and so on. And in the last two, this week's problem set and the one before it, you have been looking at PSNR for different processes applied on the image. If we become more specific in what we are really addressing in our discussion, what kind of degradation, what kind of processes. We are looking at blurring, we are looking at geometric distortion, shrinking, zooming, applying some kind of a geometric transform, or networking losses when you are losing certain parts of the image or the video, or because of applying really a very compression algorithm with high compression ratio, then you will have some kind of a blockiness artifacts. And we'll talk about those once we talk about coding. So these are more specifically the degradation that we're already addressing in this discussion. So now let's talk about subjective and versus objective. So in the subjective one is really the ultimate one. So if you really want to find the correct quality of an image, then you have to have a group of human beings who are really expert in imaging, sitting and evaluating those images and scoring the quality. And so that's really kind of the ground truth, the ultimate measure, quality measure. However, it's very obvious you cannot really have enough time and human hours to really evaluate all those images. And in real-time application, it becomes extremely impossible to do that. So we have to really resort to objective measures. And an objective measure, you have really two approaches. And the first one, from the computational neuroscience folks, we have understanding of some the attributes in the human vision system, and not really build up based on those. And eventually, what we would like to lead to is to have a mathematical equation that incorporate the human vision system attributes into the equation to have a quality measure. But in some cases, as you have seen in the PSNR and the mean square error, we cannot really have, we don't really have an HVS dependency. So as you're looking at the image at just basically two matrices, and you are comparing these two data points with each other. So before we dig into the objective measures, let's really study the subjective assessment. And there are really two ways how we run subjective assessment of images, two major ones. So the first one is, we call it a single stimulus method. Basically, from the name, you have a bunch of images, the test images, and then there are some standards, ITU and IEEE, they have specific standard about the room lighting, the ratio between the display size and the distance between the display and the human. And we used to have this setup ready and on our campus when we had a big project on this quality years back. But the idea is that you have some specific environmental and display conditions. Once you have those in place, then you start to show and display a single image at a time to the observer. And then the observer will score each image, showing according to some scale we'll talk about in a minute. So after you have, and randomly you really show these images, the test images, one by one to the observer. Then for each observer, we have an opinion score for each image. If you have 20 of those observers. Then you really average among these 20 scores for that particular image. That becomes the MOS, the mean opinion score for that image. The remark in here is really about the contextual effect. It's whenever we look at just an image, a single image by itself, our background, our history in viewing images, and our experiences in life, and so on, we get some biases when we evaluate such images in terms of quality. So there's some bias there among these observers, and the scale that we use, it has a five levels. One is the worst, and 5 is the best. 5 means this is an excellent, high quality, and what we have in red there is a way. It's very difficult for us as a human to say what is really bad, what's poor, what's fair, what's good, what's excellent. So as a guide to those who are scoring the quality, we have these kind of definitions. So number 1 means there are some artifacts, some degradation in the image that are very annoying. So they are really very annoying to the individual. And then if these annoyance resources are tolerated, we call it annoying, then that's poor quality. If there are some distortions, they are slightly annoying, that means, so they are really kind of, they're not overwhelmingly in the whole image, then that's slightly annoying, that's fair. And there is some observed distortion, but it's okay. Then that's a good quality. And if I cannot see any distortion whatsoever, then that's an excellent quality image. So this is kind of a guideline to the observers in their assessment. So in addition to the single stimulus method, we have also a double stimulus or a two stimuli method. And in here, instead of showing one image at a time to the observer, we show 2 images. And remember, among these images, we have the references as well. So the distortion-free images. So here's an example of the two methods. So we have, in each case, we have 5 users. So we have 5 users, A through E, and we have 3 test images. And user A, we show user A the first image. The score is 1. The scale is 1 out of 5. We show the user test image 2. He or she scores 3, and so on. And test 3 image 3 score is 5. And then do the same thing for the second user, and so on. Of course, there are some guidelines about. We don't really show 3 images usually. Sometimes these are in the tens, if not in the hundreds of images, and we have to give a break every certain number of minutes because of the fatigue in the eye of the observers. But in general, here are the scores. And then if you take the mean opinion score, so you average for each image, you get 8 out of 5. You add. So you add this 14 out of 5, this is 19 out of 5, 23 out of 5. And then in the second one, which is the most common one, you show 2 images at the same time. So now you have a reference. You're really comparing two signals, 2 images next to each other. And now you have some reference to really guide your scoring process. And because of that, including the reference image, we have a score for it. So now we have the difference mean opinion score. And this is basically mean that I'm having how far I am from the score of the reference image. So the score of the reference image, there are 2 users who gave it 4 out of 5. So it's not really 25 out of 5, it's 23 out of 5. So how far I am from. So this is 8 from 23, that will give me 15. This is 14 from 23, give me 9. This is 19 from 23, that's 4. So you can see the lower the DEMOS score, that means the better quality I am. That means I'm very close to the reference image. which is the distortion-free image. So this is kind of if you look at databases that that deal with image quality assessment, then the ground truth that's really provided, if you choose this topic to be your project, the databases you will be dealing with, either the live or the TID or some other databases, usually they will provide the DMOS scores. And then these are the guidelines I was talking about. I think the latest was 24 participants. I think that may be increasing with the resolution, but it's something 24 to 36 participants. And it's really difficult. We did a study years back, and it's not easy for individuals to sit down. We had to bring them back like on over 3-4 days, and each time they spend total 2 hours, but there are breaks in the middle. So it's very, very time consuming. So although the number may appear small, 24 participants, but their effort is really is tremendous in this case because of the fatigue and the time they spend. So let's really move to the objective measures and dig deeper into those. So whenever we talk about quality assessment measures, there are 3 different classes or categories that we are talking about. So the first one is the for reference. For reference meaning that I have the reference image which has no distortion, no degradation. That's my perfect image, and then I have the distorted or degraded or compressed or processed image. And if I have access to both, then I can really deploy for reference methods. Although in practice, in many cases, you don't really have access to the perfect image, but this kind of the most common algorithms are the for reference. They give you a very good understanding of what would be the best features to deal with in coming up with a quality measure. So imagine that, for example, if you are let's say like a display, like for example a tablet company, and then you have some kind of streaming application running, and then like Netflix or YouTube, although they have their own quality service on the video compression, but you want to make sure basically whatever is being displayed has really good quality that really matches the display in the tablet. In this case, you don't really have access to the reference video, right? Before streaming, before compression. So you don't have access to that. What you have too is only the displayed video, and maybe you have access to the bit stream. So the bit stream that really represents the signal or the video. So in that case, you have access to some kind of elements, some kind of attributes about the reference image or video. We call that a reduced reference. So this is the one in the middle, a reduced reference. So you have the distorted, the processed, the displayed video or image, and for the degradation free or distortion free or the original video or image, you have some kind of you have some features about it, you have some attributes, but you don't really have the pixel values. So in that case, we have a reduced reference. So in many cases, in many applications online, on the literature, you see basically those attributes more or less are the bit stream that represent the compressed signal. And finally, which is really kind of the ultimate category in here, when you have no reference, meaning that you have only access to the degraded, the distorted image. So there is no reference in this case. So in here, there are some very novel algorithms there. You look at, there are something called natural scene statistics, NSS, in the signal that they have to satisfy these, and so on. So one of my former students, his PhD was developing video quality assessment algorithms And then on a remote repositioning project that I showed maybe in the first lecture, we had a golf cart really moving around the campus in an autonomous fashion, but we have an 800 number kind of driver in the cloud who will intervene when needed. And one of the criteria was really kind of to assess the quality of the captured video, to make sure basically the analysis we are doing on the videos captured by the cameras on the golf cart are really done on a reasonable quality video. So we really need a no reference quality measure. And he managed to look at the natural scene statistics, but also in his work, in his thesis, he mainly looked at the motion field in the video. So over 10, 20 frames, how is the motion, and is the motion basically modeled as we expect, or is a deviation from it? And that was really very good, and was a huge correlation with the full reference version of the video quality assessment. So there are ways where you can really come up with such clever no reference quality assessment. Here, this is an illustration, just a quick diagram of how things look like, and really nothing new compared to the previous slide. So let's look at the first one that you're already familiar with is the mean square error. You take two images, the reference image and a degraded image, and then you do point by point, pixel by pixel, the difference, square, sum, and average, and that will give you the mean square error. And this is the PSNR. And as you can see from this calculation, it doesn't really care about anything else other than how you can compare point to point. So you can imagine if you take an image and shift it by just 5 pixels to the right, to the left, or the south east, then you start comparing pixel by pixel, then you are really having difficult time to have a good quality. Although the perceived quality is almost the same, it's not really affected, but this mean square error, or PSNR, is really comparing point by point. But in general, there is the correlation with the human vision system is very poor. And then as a guideline, why we use MSE, why we have been using it for many years, because it's very simple to calculate, is real time. And then we have kind of a general understanding of, if we have something around between 30 to 50 dB, I would say with nowadays high resolution, I would say 35 dB and above, then you have a good quality video or image. And if you have something below 15, that's really poor quality, that's a low quality. And between 15 and 35, or between 20 and 35, those numbers, it depends on what the content is. It's really high motion, or there's a lot of flat region. So it depends on that content in the image or in the video. So there are quite a bit of limitation in terms of correlation with the human vision system. And what I'm talking about in the last bullet, this masking phenomena, we'll study this in more detail later in this lecture or next lecture. So one of the major issues is that if there is an error or a difference between the sum of the pixels in one image compared to the reference image, even if we don't perceive that difference, if we don't perceive that error, the PSNR will account for it, because they're just comparing numbers with each other. So that's what really kind of trying to have the human vision system based measurement algorithms try to fix. So here is from the original SSIM paper, this diagram in here. And this diagram is showing for each one of these images, showing 3 measures, the mean square error, the SSIM, we'll study this later on, and then the complex wavelet SSIM that's really an extension to SSIM. what we need to worry about at this moment is only the first number, the MSE. So if you look at the first image, this is the original image. So you can imagine this is the MSE is 0. And then all the next images, they all have some degradation in some way. Right? And now what I want you to look at is look at this image, for example, and this image here. Right? Just these two images. And obviously, I'll say for most of us, if not all of us, the image on the right-hand side has a lower quality, at least a lower perceived quality than the one on the left-hand side. However, the MSE values are the same, or very close, like 306 and 309, very close to each other. This one is also 309. So you can see that the MSE is giving the same score to both of these images, but the quality is there's a big difference in the quality. It can be even worse if you look at this image here, F. There's 309, but you can see the many of the attributes and the features in the face are not there anymore. And even with that, the MSE is the same as what we have for these two images. And you can really go through everything. Same thing in here, 308. And then look at this image in here. So the MSE is 694. That means what this number supposedly is telling us, that this image here, this image here, this image here, and this image here, and this one here. All of these 5 images, they have higher error than the first 6 or 7 images. And the reality is that it's not. It's the other way around. So basically, this is the perceived quality in these images is actually better than the first few images, the ones in D, E, and F. So you can see this is kind of just to convince you that the PSNR, the MSE, is not really does not correlate very well with the human perceived quality. And that's basically what really motivated the community to come up with alternative measurements for the quality. And one of the most common ones, and it's simple in terms of calculations, but also it has a higher correlation with the human vision system and the perceived quality than PSNR and MSE. And this one is SSIM for short, and it stands for Structure Similarity Image Quality Measure. So SSIM is a full reference measure, and the main core concept is that Al Bovic in Austin and his group are the ones who came up with this measure. And the main concept is that the human vision system extracts structure. Structure is extremely important to the human vision system. So how can we measure that? So here's the black diagram for SSIM, and the detailed paper, I have it on Canvas as well, posted for more details for those who like to dig deeper into SSIM. So again, it's a full reference. So this is our reference image. This is our degraded image. And then we have three processing blocks. So the first one, calculate the luminance, the contrast, and then what these are really doing, we are really doing the structure, right? And then what the next one is, we have some comparison, and then we have some pooling, right? So now, after you subtract the average, what you get input here, that's basically the contrast measurement. After you normalize, what you will end up with after you bring the mean to 0 and the standard deviation to 1, what's left is the structure. So we have a luminance comparison, we have a contrast comparison, and we have a structure comparison. And then we have the pooling, and we will know in a minute what that means. So the first one is how we can compare the luminance. So the overall, let's just imagine that we are really processing this for the entire image. and we look at the mean value for image F and the mean value for image G. So what this means, I'm looking for a luminance function of F and G, and that luminance function is nothing but is a function of the mu F and the mu G, which are the mean values in these two images, F and G. One of them is the reference, the other one is the degradation. And that function is given by the following. You look at C1 and C1, this coefficient is just to avoid dividing by a 0. But just look at the 2 mu F times mu G divided by mu F squared plus mu G squared. So if you have F and G are identical, then this ratio becomes 1, right? If one of them is nothing but blank, it's all basically zeros, then basically this range is what? It's 0, right? This coefficient is a 0. So you can see the scale is between 0 and 1 for this in here, and is the cross product between the mean values F and G. And F and G can be the whole image, it can be blocks of an image, as we'll see in a minute. Similarly, we can do the same thing if we remove the mean value from each one of the images, and we compute sigmas. So F minus the mean value square, and then sum average, that will give us sigma square F, right? And if you take the square root, that will give us sigma F, and the same thing for sigma G. So we're trying to look at the contrast between F and G. This is the contrast between these two values, two numbers, sigma F and sigma G. And now the same equation to compare these two together. Again, C2 is just to avoid dividing by a 0. And then we have 2 sigma F, sigma G, sigma square F, sigma square G. And they get the same thing. If they're identical, then we have and the number here becomes 1. And if one, they are very different from the other, that will be scared as well. So this is another quantity in the SSIM. Now, after you subtract the mean, and after you normalize and divide by the sigma, what you will be left with, so you have all the variations are gone, right? What you will be left with is structure. So now what's left in the F is structure in the image, and what's left in G after you subtract and normalize with sigma G, what's left in G is nothing but the structure. And now we'd like to really compare these two structures with each other, the structure in F and the structure in G. And we look at the cross-correlation coefficient, sigma FG, as the main coefficient. Again, C3 in here is just to avoid dividing by a 0. And we look at sigma F and G, and if they are really highly correlated, then what we are looking at is 1. That means they are really identical. And if there is no correlation whatsoever, then they are orthogonal to each other. And remember, the cross-correlation coefficient, it's if you look at these two as vectors in the space, then we look at the angle, the cosine of the angle between the two in here. And there is this representation. I'll come back to this one in a minute. So this representation here is really from the original paper. It's a very good representation. So imagine you have in a 3D space, you have your image X is represented by this point in a 3D space. And this 3D space, one axis is about luminance, the other axis is for contrast, and the third axis is about the structure, right? So an increase in here means that I'm changing the luminance. An increase across this axis, that means I'm increasing or decreasing or changing the contrast. If I subtract the mean and normalize, that means basically I'm bringing the mean to a 0 and bring the contrast to sigma to be equal to 1. Then I will be operating on this space, this triangle space, which is the structural plane in this 3D space. And this structural, basically all the images with the 0 mean and a normalized sigma, they all have a point or projected on this 2-dimensional plane. And now how different they are from each other is really all about how different the structure is from each other. And we look at basically the angle between them, or the cosine of the angle. And that's what the cross correlation is all about. So now what we have three numbers, three quantities. One about the luminance, the difference between the luminance. One about the difference between the contrast. So why not use edge detection for structure? So edges will only give you, so if you just want to use the edge maps, if I just shift the image by 5 or 10 pixels, right? Then I'm all of them telling you about where the localization of the edges, but I'm not giving you information about the overall structure in the image, right? And that's really what's really kind of the whole idea in here. Even if I shift the image, then these numbers that I'm talking about in here, luminance, contrast, and structure, they will not be affected because I'm looking at the overall, not point by point. Whenever you have the edges, and still you are really comparing edge to edge. You're still having that point. And there are some algorithms where you can use the edge map to improve SSIM and other methods in image quality assessment. So I was saying that you have the luminance number, you have contrast number, you have structure number. And now one way to say, I will just multiply them with each other, right? So that's my measure. And here is the slide before, a generalization. And usually this is really common in image quality assessment. I have the luminance to the power alpha, and I have another exponent for contrast, and another exponent for structure. So now all these exponents, and the purpose of these is to say, do I want to add more weight to the luminance or to the contrast or structure, or to maybe luminance and contrast but not structure, or more to structure but not contrast? So this is a design parameter. It depends on what kind of image you're dealing with, but the de facto, the default SSIM method in the original implementation and in the image processing toolboxes, all these exponent values, they have the same weight. They're all equal to 1. And we have an expression for constant 3, and this becomes the SSIM. So this is really kind of the SSIM expression that we will be dealing with. And remember, because of the contrast and the structure, you have in the numerator, in the contrast, you have sigma F times sigma G. So those will cancel out with the structure one. But if you just put the three terms next to each other, this will be the expression that we have for structure similarity. So if you look at the way we calculate structure similarity, we look at blocks, and then we have for each block we have an individual SSIM value, and then we average over all the number of blocks we have in the image. Now, what is the size of the block? It's again design parameter, design number. So for SSIM, and these are so there is a metric and there is a measure. So in this case, this is SSIM is a metric because there is symmetry. There are some equality measures that don't really have, they don't satisfy all these conditions that we have in here. SSIM satisfy these conditions, and this is one. So as in PSNR, PSNR of F and G is the same as the PSNR of G and F, the same thing in SSIM. If you compare F with G, the same as comparing G with F. The other thing which is really very important compared to PSNR is this bounded measure or metric. And the idea in here, for example, if I tell you there is an improvement in the quality of an image in the PSNR by 2 dB, it's really difficult to quantify what that means, or to add a meaning to what the 2 dB improvement means. And here we have a bounded measure, which is between 0 and 1. So if there is an improvement by 0.2, for example, then you can have some kind of an impression about how much improvement you have in the quality of the image. And of course, in here there is a unique max, and there will only be the value equal to 1 if and only if f is equal to g, or right, they're identical to each other. So back to our this is from the SSIM paper. Just look at the SSIM, not the complex wavelet SSIM. So the first image, because these are identical images, there is no distortion. So this is our reference image in A. So this SSIM value is equal to a 1. And then if you look at the next two images, we are still in 0.987, very close to 1, 0.928, very close to 1. And this one here, we have a distortion is 0.576. This one is 0.73. This one is 0.58. Yeah, so not like before. We have when we are close to 1, that means high quality. When we are close to 0, that means we are in a bad quality image. So this one is taking us away from 1. So that's a good thing. And now in here, this is 0.641. And now we can start to see where are some of the limitations, right? So you have the 0.505 here, which looks a good image. This one 0.404, 0.399, 0.549, and 0.551. So you can see overall SSIM in this case here and in here, it really worked better than PSNR. But now, once we start to compare these, there are some differences between these images that the SSIM is not really capturing very well. And that's why we have many IQA methods that were developed on top of the SSIM, and one of them is the complex wavelet SSIM that are really taken into account how we see things as a human vision system. But the concept is the same, that the structure is extremely important to us as humans, and this was really kind of the impact of SSIM. It showed that when you worry about structure, you have a much better description of the quality in the image than SSIM, than PSNR and MSE mean square error. So that's why it's such an impactful measure. So now, with that in mind, so we started basically kind of the general rule is really to apply subjective quality assessment, meaning have humans scoring the algorithm, the quality of the images, and then start to kind of look at what are the common ones, mean square error, PSNR, and then SSIM to bring this concept of structure to the mix. So now what's next? The rest of this lecture and the rest of this whole topic, image quality assessment in this course, we will look at how the human vision system, some of the features that we understand in the human vision system, and how can we really borrow these into designing such error sensitivity measures to measure the quality in images. So the first thing we look at, we look at this kind of refer to error sensitivity measures, and this is kind of the family where PSNR and MSE really belong to, which are the normalized least square error, meaning that you have a signal f in here as the reference image, you have f prime as a degraded representation of the image. Okay, there's a question. Okay, so no, when you bring the mean to a 0 and bring the standard deviation to a 1, you normalize it. And now you do it for f and you do it for g. And now what you have left in f and g is nothing but the structure, the overall structure. Now how you compare them? In the SSIM comparison, we look at the cross correlation. And you look at a three-dimensional representation of an image in a 3D space. And 3D space is the three axes are luminance, contrast, and structure. So now That's one calculation. If you compare these two normalized zero mean representation of F and G, then the cross correlation will give you one number. It's not the structure is one number, but there are other ways how you can really compute the correlation between the two images. Not the structure still is there as a two-dimensional space. You can take any image, subtract the mean, take the standard deviation, and you can see basically all the small variations are gone. And then now you have the relative intensity values between different edges and uniform areas of the image. But that's the idea: is the cross correlation will give you the number, single number. So these methods that look at the least square error or the normalized least square error, where MSE is belong to, they are usually very easy to compute, and the problem with them, they don't really correlate with the human perception. So now this is more of a really reiteration of what I was talking about before. So the first thing is whenever we look at an image, we as humans, the very basic principle, we don't look at the images as pixel and pixel. We don't look at them as pixels. We look at them overall. So we have an overall multi-scale way to look at the whole image, including yes, in V1 and V2 areas, we look at edges and we look at boundaries. And then as we move up the vision cortex, then we bring color and then we bring context. So anything that really deals with pixel by pixel comparison doesn't really represent how we perceive quality as a human being. Another one which has to do with the pooling, and this is really a very, very major issue in all image quality assessment methods, which is number 5 in here. We don't, as humans, look at an image and right away we give a number to it. We say, I want to represent the quality in this image using single number. Is an impression, is an overall we are satisfied with the quality or we are not. So this idea of pooling at the very end in our objective quality assessment methods is problematic because we are interested in having a single number. So this pooling really reduces the dimensionality of the entire space for quality to a single number, and that's a problem. And as a limitation, I will have some examples later to show you the limitation there. And then the number 4 in here, this is true if you have two different images and they have different types of errors, different types of distortions, then is it fair to compare them in the same subspace? So all of this really kind of motivated everybody to come up with different ways of how you can measure this quality. And here is just examples of very different types of distortion applied to the same images. This is the original images on the left-hand side, and the 3 ones on the right-hand side in both rows. These are resulting from different distortions, completely different distortion, different processes. And you can see they were assigned, or they had the same MSE value, more or less, same PSNR value. And that's a problem, right? It's although the perceived quality is really different from one to the other. So most of our study next will be many, many years of really different researchers who studied the human vision system. And there are certain features in our human vision system that we will be looking at in our study of IQA, or image quality assessment methods. So the first one is that the cone cells and the ganglion cells, they are not really uniform. So distribution, so we're not looking at this at every single pixel. It doesn't matter where they are. It depends on where our gaze is. They are not have the same weight in our perceived or perception of the quality. So this kind of our fixation will determine basically which pixels or which region in the image should have higher weight and which one should have lower weight. And that's difficult, right? If you want to, there's quite a bit of study in the salience detection about this whole idea of fixation and attention in the human vision system. But this is the general idea. And also the second one is our human vision system is very capable of adapting the mechanics in the eye to a wide range of intensity values or a wide range of lighting conditions. And you can, all of us experience that when we have a dark room, enter a dark room. It takes some time before we adapt. So this kind of adaptation that we have in our vision system, it can be a tricky one. And that's basically something even for those who look at as subjective studies of quality, how long you want to show that image to the observer before they have to enter their score, right? That time is very important because if you have infinite number of minutes, then yes, definitely they will figure out some distortion, especially if they are experts in the field. If you give them just a very short few seconds, then that's basically the overall impression without any adaptation to the content in the image or the brightness in the image. So that's another tricky one. And then we have this contrast sensitivity function that's already part of our human vision system. And this contrast sensitivity, either in the spatial domain, and we'll see those in more detail, or in the temporal domain. So when we have some motion in a video, for example, there is that kind of contrast sensitivity, which leads us to talk about masking. Masking is an extremely important feature where if you have a certain features in the image, and there are two types of features, and there are certain features, depends on the frequency content, frequency band where they belong to, where one feature will be able to mask another feature. And that could happen in the spatial domain as well as in the temporal domain. So this masking effect, as you can see in what we've studied so far, either is really MSE or SSIM. We don't really account for any of these. And then finally, what I talked about, pooling. This pooling process, we are really pushing our quality measure, objective quality measure, to come with a single number for the quality of an image. That's really a problematic step. So, so here is kind of like a wish list of what we would love our image quality assessment method to account for, and this is just a subsample of a longer list, but these are kind of the ones that everybody agree on, that at least these ones, if they are in one quality measure, that's really fantastic, but they're not really easy to put them all together into one. So so let's just look at some basics and look at the OTF. This is the optical transfer function, right? And if you have any optical system, if you input to it this periodic grating on the left-hand side, you have between black and white just perfect signal. You have 100% contrast, and then you have some distortion in this optical system. And then the output on the other side, you will have basically this kind of imperfect transition between black and white. And now your contrast really reduced by 10%. So you have 90% now. So now if that periodicity in the input grating is different, as in this case in here, again, the input have this 100% contrast. And now you have a different optical system, you have different distortion, and then you get this as the output. And now what you had as 100% contrast in the input signal, what you have in the output, you will have 20% only. But you have this kind of resolution or contrast, which is 20% only differentiate between white and dark or black. That's a problem. That's a very serious problem, because now you have this contrast sensitivity is in this optical system is problematic. So So what was next? I'm just throwing at you the concepts that reflect on each one of these, and just to tell you what we're talking about. So here's the OTF first, and the next one is the point spread function. That basically, when you are looking at a specific image, a specific location, then we have this non-uniformity in our cells. Looking at those images. So, and here is just a representation of that in a two-dimensional space. So, as we move, the center will also move, but you can see basically how how difficult it is to model this to have a general image quality assessment for the entire image, which is like can be 1024 by 1024 pixels, for example. And then we look at the MTF, the modulation transfer function. And this is the idea in here. If you look at, take the x-axis as your spatial frequency, how much frequency you have, and then your y-axis is this sensitivity. Basically, how much resolution you have, can you differentiate between these bands. So what you can see, the best one, just look at from this diagram in here. This is spatial frequency, how many cycles per millimeter. And this is basically our sensitivity between 0 and 1. At the low frequency, we have really high sensitivity. And then that will keep dropping, keep dropping until we get to high frequency. And that's basically how sensitive we are, or an optical system in general. And that's basically the modulation transfer function. That's basically the optical system. It's what we talked about before, which was the optical transfer function. Here is just a sub category of this one. So there are, as you can see in here, if we keep in mind that the spatial frequency or temporal frequency later on, that spatial frequency, it depends on what that magnitude of it, then how sensitive we are to it. So in that case, if there is an error in a certain band, then maybe we are not sensitive to it, so it's okay. So our quality measure, because we cannot perceive it, our quality measure should not be account for it. So this is the idea that we are really talking about in here. How can we empower our mathematical equation, the image quality assessment method, to account for what we can perceive and what we cannot perceive, right? So if you take that wavelength into account, so what I showed you before in the previous slide is just this curve here. But now if you add the wavelength as another axis, it depends on the wavelength that curve shape can change, right? So it depends on the wavelength is also a function in that. So if you can have a wavelength plus the spatial frequency, then we have a much better idea about how sensitive the optical system or the human vision system to the signal. So these are just examples of what are the things we may look at. So if you say, what are really the major blocks I need to have in my image quality assessment if I want to come up with the best perfect image quality assessment method? In general, these are the major blocks. So the first thing is you need to do some pre-processing. You need to do some contrast sensitivity filtering, decomposition, normalization and masking, and then pooling. So these are kind of the major blocks that you have to worry about. So now what's next? We'll study each block and then just to give you some examples of what you could implement and why in each one of these blocks. And this is the part of the course where we move into more onto the algorithmic side, away from the math side. And later on we have DFT, we have denoising, we need to go to the math again. But this is kind of part where, that's why image quality assessment is really more of an art. There's a big art component as well as math and engineering component, because there is quite a bit of philosophy as well in it. So in the pre-processing, it's no-brainer. If you can really register both images, align them together, so you're comparing them properly with each other. And then if you could really transfer the color into something that really has like LAB, for example, or HSB, where it can fit the human vision system. And then if you could, which is really difficult, if you can incorporate what the display at the very end here, right, where the image is being displayed, if you can incorporate some of the display device parameters into the image itself, so that way you know exactly what the final viewer is looking at, and that's really difficult. There are quite a bit of researchers, friends of mine, especially in Europe, who have amazing capabilities in their labs, where they have tons of different devices and displays, because the resolution, the technologies, plasma, LCD, and so on, have an impact on how we perceive the same signal, same image, same video. And there's quite a bit of research being done by those folks, especially one of them is in France, two of them in France, doing quite a bit of good research on that aspect. And then if we'd like to implement if you divide your image into blocks, for example, then we'd like to have a PSF, a low-pass PSF, basically to focus on the center of the block and less weight to the surrounding or the edges and the boundaries in the block, for example. And then how we can really simulate light adaptation, where we can convert these into what we refer to as the contrast stimuli. So these are all ideas for pre-processing, but the major ones that we really look at is this alignment that we always do, the color space, we always do. The rest in here, they are not really straightforward. We can do PSF if we have small the blocks of the image, but the first two are really the most common ones in the literature. And then next, we will look at this contrast sensitivity function, CSF. So this diagram in here, this figure, what you need to worry about is the x-axis as before. This is frequency, spatial frequency, and this one's sensitivity. What we are trying to do, we give this to a number of human beings, and we tell them basically mark where you cannot differentiate between different bands anymore, meaning that inside here, I can detect the spatial frequency. Outside in here, I cannot see a difference. So basically this whole area outside this red curve is uniform to me. I cannot really differentiate between these two. So usually the CSF curve will always look something like this. And now this here is telling you what? So this one here is telling you that there are certain spatial frequency that are visible, and there are some of them are invisible between these spatial frequencies. So you can think of this as a band pass filter. So you are really, as a human, most sensitive to the intermediate range of spatial frequencies, and we are really this sensitive to the spatial frequencies, especially on the higher end as well as on the low end. So this gives quite a bit of information about where you want to focus on in terms of having a good representation, good quality. Maybe for this area, you don't really have to worry much about it. This one, you worry a little bit less than what you have in the band pass. So that's why your contrast threshold basically is being represented here as you go lower and lower from on the y-axis. So this is really the second block diagram that we have here, which is the contrast. If you know this information, you have a decomposition algorithm or a transform of the spatial frequency in your signal, then with the CSF curve in here, then you know basically where to emphasize in terms of the content. One of the things that we have to keep in mind, this idea, the CSF is not really is the MTF for just a single kind of neuron. Is really there is an envelope. So what you can think of the CSF in here is an envelope, and our neurons basically they have small band in between. You can overlap even. So now we can think of this. What this is telling us, if we can really have a decomposition algorithm in the frequency domain, give us these small bands, right? And then each one of them, they will have this kind of sub-band CSF functions that will construct the overall CSF that you have to worry about. This actually gives us really quite a bit of capability in designing our image quality assessment. And you can think of this as those small, the low frequency content. They give you information about the large objects, like the shadows, gradual changes, intensity across the image. And those in the higher band ones will give you basically the finer detail, the fine grain basically details. So now you can see which ones basically you want to emphasize in your image quality assessment algorithm. And this leads us to the next, maybe it's here, yes. The channel decomposition one. So in the channel decomposition, we have 4 minutes. So in the channel decomposition one, what we're really interested in is to really kind of decompose and separate the visual stimulus into different spatial and temporal subbands. And for now, at least, we're into spatial subbands. So they are really Gabor filters has been kind of very common ones. And what we're really showing in here, these are all different decompositions. So Lubin, Daly, Watson really worked quite a bit on this. What is really the best decomposition they could do? We'll study a little bit about wavelets, and then we'll study quite a bit about DCT. So all of these are in the frequency space, frequency plane. And now, how can you come up with these decomposition in the frequency domain? Because remember, each one of them is as if it's really as a reaction to a neuron in the human system. So we'll have our own CSF profile for each subband in this decomposition model or decomposition subspace. And here are some just information about what this decomposition looked like. So this is the first channel. You can see quite a bit of number of edges and so on. This is number channel 3. You have finer details being imposed in here. And then as you go to channel 6, and so on. So I think I'll stop here. Let me see if I want to say something. Yeah, I should stop here. Okay, so I'll stop here, and then next time we will pick it up from here. We'll study the CSF, and then we look at masking, which is extremely important. And then it's a little bit confusing now because we are really talking about many different things in the human system. But when we talk about how can we use all of this to design PSNR-HVS or PSNR-HVS-M, and you can see how we can borrow this information about our understanding for the human vision system in designing, improving the PSNR. Then I'm hoping that will bring everything together. And then after that, we'll study how, if you have a quality measure, how do we evaluate and validate if this is really working or not, given a ground truth and subjective measures. So this is the first lecture. I think it's a little bit confusing, but it's a very intriguing subject, and hopefully it will become really clearer and more interesting to you next week. We have a few papers on this subject as a term paper. So far interpolation, and then now we have this quality measure. So already posted on Canvas. I put quite a bit of number of papers there. Some of them are short, some of them are really long, but I'm hoping they add quite a bit of resources and references to you about this part of the course. And the next homework problem set number 4, it will be only about image quality assessment. So by Tuesday, I think by now you should be able to solve at least 3 of the 5 problems. By Tuesday, I think you should be able to solve all 5 of them. All right, thank you, and we'll see you next week. Bye-bye.